All right, today we are going on a journey. We're shrinking down, way, way down, past anything you can see, to find the strangest and strongest glue in the entire universe. These are the particles that literally hold reality together as we know it. So, let's get into it. Okay, let's start with the familiar. Everything, right? You, me, this planet, the stars, it's all made of atoms. We've known that for a while. But what's going on inside them? Well, right at the very heart of every atom is this tiny, super dense nucleus. And packed inside that are protons with their positive charge and neutrons, which have no charge. But we can go even deeper. Because if you could crack open one of those protons or neutrons, you'd find they aren't fundamental at all. They're made of even smaller particles called quarks. These are the real, honest-to-goodness building blocks of matter. And that brings us to the big question. You've got this little proton packed with quarks. What's holding them together? I mean, why doesn't the whole thing just poof, fly apart in an instant? The answer is a force. But not just any force. This is a force so ridiculously powerful that it makes things like gravity and electromagnetism look, well, kind of feeble in comparison. It's called the strong nuclear force, and it is, without a doubt, the universe's ultimate superglue. And the particle that carries this incredible force, that's the star of our show today, the gluon. It's this tiny, massless particle, and its entire job, its whole reason for being, is to carry the strong force and literally glue quarks together inside protons and neutrons. You know, the name gluon isn't just a cutesy nickname either. The physicist Murray Gell-Mann came up with it way back in 1962, because that's exactly how he pictured it, as a kind of cosmic adhesive holding the universe together at its seams. Now this is where things start to get really weird, because the strong force doesn't play by the rules we're used to. It follows this bizarre set of principles based on a property that physicists, in a stroke of genius, decided to call color. And if you want to understand why this force is so profoundly different from, say, magnetism, it all boils down to one thing: the kind of charge that the force-carrying particle has. Think about it like this. A photon, right? It carries the electromagnetic force. Light, radio waves, all that. But it doesn't have an electric charge itself. It's neutral. A gluon, on the other hand, is totally different. It carries the strong force, but it also carries the charge of that force, this color charge. And that one little fact changes absolutely everything. Because gluons carry this color charge, they don't just interact with quarks, they interact with other gluons. They are constantly sticking to each other, creating this complex, sticky web. That is something photons simply do not do. So this leads to a neat little puzzle. You've got 3 colors, red, green, and blue, and 3 anticolors. So you might think, okay, 3 times 3, there must be 9 different kinds of gluons, right? Makes sense. But there's a catch. One of those 9 possible combinations actually cancels itself out perfectly. It creates this colorless state. And if a particle is colorless, it can't carry the color force. It's like having glue that, well, isn't sticky. It just doesn't work. So you take your 9 potential gluons, you subtract that one useless colorless combination, and you're left with the real number, the number of active gluon types that are actually out there doing the hard work of binding our universe together, is 8. Now, this whole idea of gluons sticking to themselves leads to one of the weirdest and most important rules in all of physics. It's a phenomenon called color confinement, but I like to think of it as keeping quarks on a leash you can never, ever break. Imagine the field of gluons stretching between 2 quarks is like a super strong elastic band. But here's the crazy part. Unlike a normal elastic band, this one doesn't get weaker as you pull it. The force stays constant, whether they're a millimeter apart or a mile apart. So let's walk through what happens. You try to pull 2 quarks apart. That gluon field between them stretches out, but the tension just keeps building. The farther you pull, the more energy gets stored in that field. And eventually, you hit a point where there's so much energy packed into that stretched field that it becomes easier for the universe to just poof, create a brand new quark and antiquark pair right out of thin air. Or, well, right out of that energy. And those new quarks instantly bind to the ones you were trying to separate. So what's the result? You never, ever get a quark by itself. You just end up with more particles. Quarks are permanently locked up, forever confined inside things like protons and neutrons. Okay, this is an incredible mind-bending theory. But the best part is, it's not just a theory. Physicists actually figured out how to prove that these bizarre, sticky little particles are real. So as we said, the idea first popped up in 1962. It took a while until 1978 for the first hint of evidence to appear in experiments. But the real smoking gun, the undeniable proof, came just 1 year later, in 1979. At a particle collider in Germany, scientists smashed particles together and saw something called three-jet events. It was the unmistakable signature of a quark, an antiquark, and a gluon all flying apart from the collision. There it was. The glue was real. So we found them, we kind of know how they work. So what's next? I mean, where does gluon research go from here? Well, scientists are now hunting for even more exotic stuff. They're looking for things called glue balls. Think about that. A particle made of pure glue, no quarks at all. And they're trying to create something called a quark-gluon plasma, which is basically a super hot, super dense, primordial soup where quarks and gluons are finally, for a brief moment, set free. And what's just mind-blowing is that this quark-gluon plasma isn't just a hypothetical idea. Scientists are pretty sure this is what the entire universe was like just microseconds after the Big Bang. And today, right now, at places like the Large Hadron Collider, they have actually recreated that cosmic soup in the lab. And that leaves us with one final, incredible question to ponder. We've spent this whole time talking about how gluons are the glue that holds our stable, predictable reality together. So what does it mean that we've figured out how to, even for just a fraction of a second, deliberately unglue the universe and set them free?